Emergence of Earth. Geological history of Earth. The Hadean Earth was at first inhospitable to any living organisms. During its formation, the Earth lost a significant part of its initial mass, and consequentially lacked the gravity to hold molecular hydrogen and the bulk of the original inert gases. The atmosphere consisted largely of water vapor, nitrogen and carbon dioxide, with smaller amounts of carbon monoxide, hydrogen, and sulfur compounds. The solution of carbon dioxide in water is thought to have made the seas slightly acidic, giving them a pH of about 5.5. The Hadean atmosphere has been characterized as a gigantic, productive outdoor chemical laboratory, similar to volcanic gases today, which still support some abiotic chemistry. Oceans may have appeared as soon as 200 mi after the Earth formed, in a hot, 100 C, reducing environment, as the pH of 5.8 rose rapidly towards neutral. This scenario has found support from the dating of 4.404 GYA zircon crystals from metamorphosed quartzite of Mount Nerrier in Western Australia, which provide evidence that oceans and continental crust existed within 150 ma of Earth's formation. Despite the likely increased volcanism and existence of many smaller tectonic platelets, it has been suggested that between 4.4 and 4.3 GYA, the Earth was a water world, with little if any continental crust, an extremely turbulent atmosphere and a hydrosphere subject to intense ultraviolet UV light from a Tauri stage sun, cosmic radiation and continued bolide impacts. Internal heating as a result of gravitational sorting between the core and the mantle would have caused a great deal of mantle convection, with the probable result of many more smaller and more active tectonic plates than now exist. The hypothesis for the late heavy bombardment posits that the Hadean environment between 4.28 and 3.8 GYA would have been highly hazardous to modern life. Following the NICE model, changes in the orbits of the giant planets may have bombarded the Earth with asteroids and comets that pockmarked the Moon and inner planets. Frequent stellar collisions with objects up to 500 km in diameter would sterilize the planet's surface and vaporize the oceans within a few months of impact. Hot steam and rock vapor formed high-altitude clouds that would completely cover the planet, making photosynthesis unviable. Rains would slowly have drawn down the height of the clouds, returning the oceans to their original depth only 3,000 y after the impact event. Impacts before 3.5 GYA would have also brought quantities of organics comparable to those produced by terrestrial sources. The periods between such devastating environmental events give time windows for the possible origin of life in early environments. If the deep marine hydrothermal setting was the site for the origin of life, then abiogenesis could have happened as early as 4.0 to 4.2 GYA. If the site was at the surface of the Earth, abiogenesis could only have occurred between 3.7 and 4.0 GYA. However, new lunar surveys and samples have led scientists, including an architect of the NICE model, to de-emphasize the LHB. If life evolved deeper than 10 meters, it would have been shielded from both late impacts and high levels of UV radiation from the Tauri stage sun. Simulations of geothermically heated oceanic crust yield far more organics than those found in the Miller-Urey experiments. In the deep hydrothermal vents Everett Schoch has found, there is an enormous thermodynamic drive to form organic compounds, as seawater and hydrothermal fluids, which are far from equilibrium, mix and move towards a more stable state. Schoch found that the available energy is maximized at 100 to 150 degrees Celsius. Precisely the temperatures at which the hyperthermophilic bacteria and thermoacidophilic archaea have been found living. These organisms are placed at the base of the phylogenetic tree of life, closest to the last universal common ancestor, Luca.